This is a video from the Chemistry Department of Queen Mary's College to give you an introduction to the way in which our model of the atom has developed over time. Here are the learning objectives for this video. So for the purposes of the A-level exam, you need to be aware of the fact that models of the atom have become gradually more sophisticated over time. You need to be able to describe that, and you need to be able to explain how evidence for those models was obtained from experiments. Now, although you won't be required to discuss this in an exam, you should be aware of the fact that the idea of the atom is actually over 2,000 years old and was first deduced by a Greek philosopher called Democritus, who carried out what's called a thought experiment. He imagined cutting up a piece of matter and realised that at some point there would reach a situation in which you would not be able to cut it up any further, and that ultimate particle, if you like, was described as an atom, a small particle that can't be split up any further. So that's our starting point for the atomic model. We're going to be looking at several further atomic models. You may, as you watch the rest of this video, want to make some kind of record of what you're seeing, and so maybe a table like this would be a suitable way of proceeding, where you may want to describe the models and any evidence that the model was based on. Now, the name of the scientist or philosopher that came up with the model is not going to be required in the exam, but it's helpful to know some of those names just because it'll make it easier to discuss the models over the next lesson or so. So we begin with the idea that there are these things called atoms, and they're small particles that can't be subdivided. And let's now fast forward to the beginning of the 19th century to see how those models were developed further. So at the beginning of the 19th century, an English chemist called Dalton developed the idea of the model further. He took the idea of the atom as being something that couldn't be divided any further, and then realised there must be several different types of atom, all with different properties, in particular, all with different masses. So each kind of atom had its own mass. Now, the evidence for that was based on more than just a thought experiment. It was based on practical information, because Dalton carried out experiments in which he discovered that particular elements would always combine in fixed ratios of masses. For example, 14 grams of nitrogen would always react with 3 grams of hydrogen. What Dalton realised from that was that an atom of nitrogen would have a different mass from an atom of hydrogen, and he could actually start to figure out the ratios of the masses of each of those elements. So far we've been thinking of atoms as being unable to be divided any further. Well, the first piece of evidence that started to cast doubt on that came with the discovery of something called cathode rays, which were invisible streams of particles that appear to have a negative charge. And you can see here the cathode rays being deflected in an electric field, suggesting that they had a negative charge. So just to clarify what was actually happening in that photograph, we've got here a metal cathode, and particles are streaming off that cathode. We now know that those are electrons, and they're being attracted towards this positive plate here. So the point about the experiment was it showed that the atoms that the metal here was made up of must have contained particles even smaller and lighter than those atoms. And it's the first idea that there must be what we call subatomic particles within the structure of the. So as a result of that, a scientist called Thomson came up with what was described as the plum pudding model, which was based on the idea that things like a Christmas pudding or a plum pudding contain fruit encased in a kind of dough or pastry, and the atom he visualised in much the same kind of way. So in the plum pudding model, we had basically these negative electrons, which are like the plums in a plum pudding, and they are embedded in this material that is positively charged, so that overall the atom is neutral, but it contains these negatively charged electrons. So here's the plum pudding model, negatively charged electrons embedded in a sphere of positively charged matter. And a reminder about the evidence for that, that's the idea that we can actually pull those electrons out by using electric fields. Now, you're unlikely to have to remember that evidence itself, but you should be aware of this model and how it differed from the simple billiard ball model. Okay, well, we now fast forward to the beginning of the 20th century, and a very famous experiment that was carried out by two scientists, Geiger and Marsden. And we're thinking here that atoms contain this positively charged matter, and embedded in it might be these electrons. Well, Geiger and Marsden attempted to fire particles through a very, very thin gold foil. The idea was that they were hoping this would only be 1 or 2 atoms thick. They were really trying to find out whether anything could get through that sphere of positive charge. So they took the newly discovered alpha particle, which was produced by radioactive atoms, and directed a stream of alpha particles through this gold foil. Now, what they were expecting was that the alpha particles might well pass through this very, very thin gold foil, because possibly that positive charged matter in which the electrons are embedded might actually be sort of fairly thin and diffuse stuff, so that the alpha particles would pass through. So what they did was to attempt to detect the alpha particles on the other side of the gold foil, and they were expecting that at least some of the alpha particles would pass straight through. Well, let's see what they actually found. They actually found that, yes, alpha particles did pass through the gold foil, but some of them were deflected slightly in a pattern looking something like this. And even more amazingly, some of them, a small number, bounced straight back. Now, these results were unexpected, and they took it to their supervisor, a famous scientist called Rutherford, and he came up with a new. So this was called the nuclear model, or the Rutherford nuclear model. And rather than imagining that the atom was mostly this kind of diffuse cloud of positive charge, he imagined that the positive charge was centred right at the middle of the atom in a very, very dense region known as the nucleus. The rest of the atom is mostly empty space, and right at the centre then we've got this small, very dense positive nucleus. Now that explains what happened to the alpha particles, because most of the alpha particles would pass completely through the empty space of the atom. Some that passed close to the nucleus would be deflected. Now, alpha particles were known to have a positive charge, so if they pass close to a positive nucleus, you can imagine they're going to be deflected slightly away from that. However, any that hit it full on, because the nucleus is very dense and contains most of the mass of the atom, the alpha particle would hit that positive nucleus and would bounce back. And that is indeed what was observed in the experiment. So, here's our Rutherford nuclear model. Mostly empty space, dense positive nucleus surrounded by electrons, and here's the evidence for it. Okay, well, here's some new evidence. And this is starting to get quite subtle now. You may have been given a chance in class to see something called an emission spectrum, and if you haven't, you certainly will later on in the course. And this is the idea that atoms are able to emit light. If we heat, say, a gas up, the atoms in the gas are able to start emitting light. The light often looks coloured. If we attempt to split the light up into what you would normally expect to see of as a light spectrum, what scientists observed was that rather than seeing the familiar spectrum containing the colours red and orange and yellow and green and so on, we saw simply very, very thin lines of particular colours, and the suggestion from that was that this atom was only giving out a very small number of different frequencies of light. Each frequency was seen as a line of colour. Now you may well wonder therefore what this idea of atomic spectra or atomic emission spectra, to give them their full name, has to do with atoms. Well, it was thought that the light was produced by an electron in the atom moving closer to the nucleus. As it moves close to the nucleus, it loses some energy, much like a satellite, say, dropping to a lower orbit, and that energy is given off as light, and that's the light we saw in the spectrum. Now, because we only see a very small number of lines, the suggestion is that electrons can only move in certain ways in the atom. It was suggested by a scientist called Niels Bohr, that this meant that the electrons might well exist in particular orbits or shells, and that electrons dropping from a higher orbit to a lower orbit, higher shell to lower shell, would be emitting light. And because there's only a small number of shells, you only see a small number of different frequencies or colours of light. So there was a way of explaining the observation about atomic spectra. That was supported by some further experimental evidence. This time, rather than actually using electrons and hopefully getting them to emit energy, scientists tried providing energy to atoms, and when you do that, you can actually kick electrons out of atoms completely in a process known as ionisation. Well, here's it happening for a lithium atom, and if you try and kick an electron out of a lithium atom, you find it takes about 520 kilojoules to remove what we call a mole of electrons. However, if you try and kick out a second electron, it takes much, much more energy, over 7,000 kilojoules of energy. And this fitted in nicely with the Bohr model of the atom, because of course once you've lost one electron, the remaining two electrons have to come from a shell or energy level much, much closer to the positive nucleus. And so there's a much greater force of attraction to the positive nucleus, and so it takes much more energy to lose those electrons. And so this was further evidence for the Bohr model of electrons existing in orbit. And so this became known as the Bohr model or Bohr quantum model of the atom. So like the Rutherford model, it has a nucleus in the centre. The electrons surround the nucleus, but the difference here is the electrons are surrounding the nucleus in shells or orbits. And each shell has a particular amount of energy. And here's a nice new word for you. Quantized means that the electrons only possess certain amounts of energy. There's a fixed number of different energies that they can actually have. And a reminder of the evidence for the Bohr model, the idea of atoms emitting only particular frequencies in their emission spectra, and the idea of this pattern of ionisation energies requiring more energy to remove electrons that are closer to the nucleus. Now that's as far as you need to go for A-level chemistry, but we should be aware of the fact that science continues to move on, and the Bohr model and the idea of the nucleus and electrons in shells has been further developed over the last 60 or 70 years. For example, it's been realised that electrons don't really orbit the nucleus in neat orbits, as we often show. Instead, you can treat electrons as being a little bit like waves, and you can mathematically deduce the likely regions in which the electrons will exist in. And so we end up with these things called orbitals. And the nucleus, which contains protons and neutrons, those protons and neutrons themselves are thought to be made up of even smaller particles called quarks. And in fact, quarks make up a very, very wide range of particles, known generally as hadrons, and you may have heard of the Large Hadron Collider. Protons and neutrons are simply one example of hadrons. But as far as your A-level is concerned, you may well want now just to check that you've picked up the key points from this video. So here are 3 check your knowledge screens. So you might like to pause the video while you look at the question and come up with an answer, and then when you're ready you can reveal the answer. So the first is about the different models and the order in which they came. I'll give them the name of the scientist that came up with the model. In an exam question, the likelihood is you would probably be given diagrams of those models and asked to work out which were the earliest. So pause the video now and work out the order in which those models are likely to come in, starting with the and hopefully what you came up with was this order here: the billiard ball model, plum pudding, the nuclear model, and finally ending up with the Bohr model. Okay, and a second chance. So this is about the experimental data that was used to support the models. So describe the key bit of evidence for the Rutherford nuclear model. Pause the video while you think about that. So what you should find is that it was all about the way in which alpha particles behaved when they were fired at a thin sheet of gold atoms. And of course the reason they do that is to do with the way that they collide with the positive nucleus. And finally, can you try and describe the key features of the most modern model of the atom, the Bohr quantum model that we've described? So pause the video while you think about that. And here they are. dense central nucleus containing protons and neutrons.